Welcome back, everybody. The question that I want to ask here is, how do we find the equations of straight lines in dimension 3 and beyond? So if you think about a straight line in dimension 3, so let's say I have a straight line in dimension 3, then it's not clear how to define the slope of such a line. So we're going to take a different route. We're going to parameterize a straight line that is, we'll be looking at parametric equations of lines, which I'm going to be explaining now. So let's say we have a straight line L, and we have a vector A that is parallel to the line L, and we are also given a point P on the line L. So P has coordinates x0, y0, z0. So whatever I'm doing now here applies to any dimension. For the purpose of this discussion, however, I'm picking points, lines, and vectors in dimension 3 here. So we want to find the equation of the line that passes through the point x0, y0, z0, and parallel to the vector A. So once again, we are given a point on the line, we are given a vector parallel to the line, we need to find the equation of the line. So what do we mean by the equation of the line? Well, we mean an equation that will be satisfied by any arbitrary point xyz on the line. So let's let capital X be an arbitrary point on the line with coordinates xyz. We are looking for an equation involving that will be satisfied by x. Well, if we look at the vector px, which would be given by x minus p, then clearly x minus p is a vector parallel to the straight line L, so it will be parallel to A as well. So x minus p is parallel to L. Well, so what that means then is that x minus p would be equal to t times A, where t is a scalar or a real number. Since because they are parallel, they must be one of them would be a multiple of the other. So then I can say that x would be p plus t times A. So this is the vector equation of the line L. So this is the vector equation. This is the vector equation of the line L. Okay, so if I'm given a straight line in any dimension, so if I'm given a point on a line and a vector parallel to the line in any dimension, the equation of that line will be given by this equation. So not just in dimension 3. So let's say in dimension 3, if P has coordinates x0, y0, z0, the parallel vector A has coordinates a, b, c, and capital X is the arbitrary point on the line xyz. So P is a given point, X is an arbitrary point on the line, A is parallel to the line. Then the equation of the line would be would be given by the vector equation of the line would be x is equal to p plus ta. Now, so this equation, if I write down the components of x, p, and a, we get xyz is equal to x naught, y naught, z naught plus t times abc. So xyz would be x naught plus at, comma, y naught plus bt, comma, z naught plus ct. So we see that x would be x naught plus t times a, y would be y naught plus t times b, z would be z naught plus t times c. So these are the parametric equations of the line passing through P parallel to A. Now in dimension 4, if I am given the point P with coordinates alpha 1, alpha 2, alpha 3, alpha 4, and a parallel vector A with components A1, A2, A3, A4, then what would be the equation of the line passing through P parallel to A? Well, given the arbitrary point x on the line, x would be p plus ta, where t is a real number. So then we see that first component x1 of x would be the first component of p plus t times the first component of a. So x1 would be alpha 1 plus ta1. What would be x2? It'll be the second component of p plus t times the second component of a. So it'll be alpha 2 plus t times a2. Similarly, x3 would be alpha 3 plus ta3. x4 would be alpha 4 plus ta4. So these are the parametric equations of the line in the 4 space passing through the point P parallel to the vector A. So this way of writing down equations of a line works in any dimension, including the 2 space. So let's say I have to find the parametric equations of the straight line in dimension 2 with equation negative 2x plus y is equal to 0. So we are given the rectangular equation of a line in dimension 2. We want to find the parametric equations of the line. And this is very easy to do. All we have to do is set x to t, and then we can solve for y. So y would be 2 times t. So if I set x to t, then I see that y has to be 2 times t. So then x would be 0 plus t times 1, y would be 0 plus t times 2. So we see that xy would be 0, 0 plus t times 1, 2. So this is the equation of the line that passes through the origin with the parallel vector 1, 2. And so you can see how we can parameterize the straight line with the rectangular equation negative 2x plus y is equal to 0. So when we look at the parametric equations of a line, t is called a parameter here. And when we draw the straight line, notice that t doesn't appear in our figure. So that's why it's called a parameter. So here I'm going to give you an interpretation of the parameterization of a straight line. Well, actually, yes. So what would be a interpretation of the parameterization of a line? Here's an interpretation. So imagine that a bug is moving along the line moving along the line with constant velocity A, and P is the position of the bug at time 0. And so the question is, what would be the position of the bug at after time t? Well, since the velocity is constant a, then after time t, the displacement vector of the bug would be t times a. So t times a would be the displacement of the bug after time t. And so if I add that to the initial position p, then I get the position x of the bug at time t. So if a bug is moving along the line with velocity a and initial position at time 0 equal to p, then the position of the bug at time t is given by x is equal to p plus ta. Okay, so let's do an example. Let's say we want to find the parametric equations of the line passing through the point P with coordinates 1, minus 3, 1, and the point Q with coordinates negative 2, 4, and 5. So here is let's say, so here is the line, let's say, and P and Q are two given points on the line, and here is the origin. So in order to write down the equation of this line, I need to know a vector that's parallel to the line, and I also need one point on the line. Well, I have 2 points, so I can pick any one of them as the given point, but I need a vector that's parallel to the line. Well, how do I do that? Well, if you look at the vector P, the vector from Q to P, well, that vector would be P minus Q, right? Because it's the tip minus the tail. So the vector from Q to P is the vector P minus Q. And so what is P minus Q? Well, P minus Q would be, you subtract the coordinates of Q from the coordinates of P. So you get 1 minus minus 2 is 3. Minus 3 minus 4 would be minus 7. 1 minus 5 would be negative 4. So A would be a vector that is parallel to the line. So I'm going to use the point P as a point on the line. So the equation of the line would be x is equal to P plus TA. So xyz would be P is, recall P is 1 minus 3, 1 plus T times the parallel vector here is 3 minus 7 minus 4. So x would be 1 plus 3t, y would be negative 3 plus negative 3 minus 7t, and z would be 1 minus 4t. So these are the parametric equations of the line passing through the given P and Q. Instead of using P, when I'm writing down the parametric equations of the line, instead of using the point P, I could also use the point Q. We're not going to get the same exact equations, but it will still be the equation of the straight line. So I want to warn you here that the equation, a given line has many different parameterizations, which is kind of clear because if there are many different parallel vectors that we can use, and there are many different given points we can use on the line. So depending on which point and what parallel vector we are using, we get a different set of equations, parametric equations. So if you change the vector A, or if you change the initial given point P, then you change the equations. But they will all be the equations of the line. Now, once in this example we came up with the parametric equations of the line, notice that from each equation here, we can solve for t. So t, if I solve for t from the first equation, I would get t is equal to x minus 1 over 3. From the second equation, if I solve for t, I get y plus 3 over negative 7. In the third, I get z minus 1 over negative 4. So these are known as the symmetric equations of the line. Now, in the second fraction here, I can put the negative on top, and in the third one, I can also put the negative on top here if I wanted to. But so once we solve for t, these three quantities will be equal. This is known as the symmetric equations of the line. Okay, so let's say P and Q are two given points. These are fixed. We want to find a parametric representation of the line segment joining P and Q. So we want to find a parametric representation of the line segment from P to Q, not the straight line passing through P and Q. We just are focusing on the line segment from P to Q. Well, obviously we know that x would be P plus T times, so if you look at, we need a vector parallel to the straight line, to the line segment, right? So, Q minus P obviously is parallel to this line segment, the vector Q minus P. So if I write x is equal to P plus T times Q minus P, and if I allow T to be any real number, then I get the equation of the line passing through P and Q. But if I want just the points on the line segment from P to Q, then we restrict T to be between 0 and 1. So notice that when T is 0, then we get the point P, and when T is 1, so if T is 1 here, then we get P plus Q minus P, which is then going to give us Q. So when T is 1, X would be Q. So one way of thinking about this is that you have a bug moving from P to Q, and so it starts at P and ends up with Q. So at time 0 it is at P, and at time 1 it is at Q. Okay, and then of course the Q minus P would be its velocity, because that's the displacement over a unit over a unit time. So what you need to remember is that the parameterization of a line segment between 2 points P and Q is given by x is equal to P plus T times Q minus P. In dimension 3 and beyond, or even in dimension 2, we define parallel lines in the following way. So if I have two lines, L1 and L2, these two lines, then we can pick points P1, Q1 and on L1, and points P2, Q2 on L2. Then P1 minus Q1 is a vector parallel to L1. P2 minus Q2 would be a vector parallel to L2. So we say that L1 and L2 are parallel lines if P1 P1 minus Q1 is parallel to P2 minus Q2. Before I forget, I wanted to mention one more thing, which is going back to the parametric equations of a line. Notice that once we write down the parametric equations of a line, the coefficients of t, a, b, c, they form the parallel vector to the line. So when we did this equation of the line passing through P and Q, so let's say we are given this parametric equations of the line, then the question asks find a vector parallel to the line. Well, we just have to read off the coefficients of t. So 3, -7, and -4, that's going to be a vector that's parallel to the line. Again, so what I'm saying is that if you are given the parametric equations of a line, and if you are asked to find a vector parallel to the line, then you can find the parallel vector by forming a vector with the components equal to the coefficients of the parameter t. Okay, so we will stop the video here, and we will look at some examples in the next video.